Gravity is the first force we ever feel. It is the pull that keeps our feet on the ground, the sensation that something massive and invisible holds the planet beneath us. It is familiar, constant, almost comforting. Yet in physics, gravity is the odd one out, a rule breaker, a stubborn puzzle that refuses to fit into the framework that explains everything else in the universe. For more than 100 years, the greatest minds have tried to tame it, to quantize it, to force it to speak the same language as the quantum world. Gravity remains silent, as if guarding a secret about reality itself. The other forces of nature behave in ways that quantum physics understands. Electromagnetism, the force behind lightning and light, is carried by particles called photons. The strong force that binds atomic nuclei together is communicated by particles named gluons. The weak force that changes one particle into another, the engine of nuclear decay, relies on heavy particles called W and Z bosons. These three forces all fit within one grand mathematical structure. They all arise from quantum fields jittering beneath the fabric of space. They all deal in discrete packets of action, quanta exchanged like notes in a cosmic conversation. But gravity plays a different game. In Einstein's way of looking at the world, gravity is not a force at all. It is the shape of space-time. Matter tells space how to curve, and curved space tells matter how to move. There is no particle that pushes the Earth toward the Sun. Instead, Earth moves along a path shaped by geometry, like a marble rolling along the surface of a bowl. In this picture, gravity is smooth and continuous, a graceful bending rather than a rattling exchange of particles. And there lies the conflict. Quantum theory demands that everything comes in discrete bits. Einstein's general relativity says that the universe is a smooth continuum. When scientists try to force these ideas together, the math breaks into nonsense. Infinite answers flood the equations, as if the universe itself screams that the two descriptions cannot be combined so easily. So physicists tried to imagine a quantum particle of gravity called the graviton. Perhaps gravity too emerges from a vibrating field like the others. But whenever they attempt to calculate the behavior of such a field at the tiniest scales, the infinities return with full fury. Even the most advanced attempts to quantize gravity have required bold and controversial reinventions. String theory stretched particles into tiny vibrating filaments, and loop quantum gravity suggested that spacetime itself is woven from discrete threads. Yet no experiment has confirmed either approach. The door to understanding gravity remains shut. This is not just a mathematical frustration, it is a deep cosmic insult. Why should one rule govern the small and another rule govern the large? The universe should not need separate instruction manuals. It should not change its laws depending on whether one looks at stars or electrons. There must be a deeper unity, a single hidden principle waiting to be uncovered. Physicists began to suspect that the real problem was not in the equations, but in the way they were thinking. Instead of asking what gravity truly is, maybe they should ask, what is space? What is time? Why do they exist? Where do they come from? For decades, these questions were philosophical curiosities, not physical ones. But then came a breakthrough that shifted the landscape. Information. Not information as in news headlines or text messages. Information as in the raw structure of reality. The fundamental yes and no answers to the universe's questions. Quantum information. Physicists had long known that particles carry properties like charge and mass. But they discovered that these properties are really just arrangements of information. When particles interact, information changes hands. The universe evolves according to rules that preserve the amount of quantum information, no matter what. Even energy may not be as fundamental as the information describing it. This insight led to a daring possibility. What if gravity does not need quantization because it was never fundamental in the first place? What if gravity emerges from something deeper, something woven from the invisible connectivity of quantum information? Something that creates space rather than merely filling it. In other words, what if gravity is not holding the universe together? What if information is? The force that guides planets and shapes galaxies might arise from patterns of entanglement. The geometry of cosmic space could be the structure of relationships between qubits everywhere in existence. Gravity may be the gentle pressure that information exerts when it tries to stay organized. If this idea is correct, then we are on the verge of seeing the universe not as a machine made of substance, but as a computation made of bits. And everything we know as physical might be the visible glow of an invisible informational network. The strangest force in nature may finally make sense once we accept that reality itself keeps track of everything. Gravity is woven into every moment of our lives, yet we never notice how peculiar it truly is. Imagine holding a coin in your hand. The entire Earth is pulling that tiny object downward. A sphere of rock over 12,000 kilometers wide exerts a gravitational influence on a circle of metal barely larger than your fingertip. And even with the strength of a whole planet behind it, gravity loses a tug of war if you simply tighten the muscles in your arm. Your hand wins. The electromagnetic forces in your body overpower the Earth without effort. If gravity were like the other forces, such weakness would make no sense. Why is gravity so incredibly gentle? It guides the dance of moons and stars, shapes the fate of galaxies and clusters, yet a small magnet can lift a paperclip against the pull of an entire world. This leads to one of the greatest puzzles in physics. If gravity is a real force like the others, why is its strength so absurdly tiny compared to them? The difference is not just a little, it is beyond imagination. The electromagnetic force is stronger than gravity by a factor of 10 to the power of 40. Written out in words, that is a 1 followed by 40 zeros. The numbers are so distant that comparing them feels like comparing a quark to the entire universe. Something about gravity is off. It does not behave as a sibling of the other forces. It behaves as something entirely separate. And here lies a clue so subtle that physics took centuries to notice it. Perhaps gravity is not weak at all. Perhaps we are misinterpreting what we see because we are trying to describe gravity using the wrong language. You would not call a shadow weak because it does not push objects around. A shadow is not a force, it is a consequence of something else. Einstein gave gravity a new face. Space and time, once thought to be passive backgrounds upon which the universe unfolds, became active participants. When a planet orbits a star, there is no invisible tether pulling it. Instead, the star bends space-time around itself, like a heavy bowling ball resting on a stretched sheet. The planet rolls along the curved surface, following a path that requires no force at all. In this picture, gravity arises because space is no longer flat. Motion is simply the natural flow of objects moving through a curved geometry. This was revolutionary. Space had become dynamic. Time had become elastic. Together they formed a fabric that could stretch, warp, and ripple like waves on the surface of a cosmic ocean. Those ripples, known as gravitational waves, were finally detected 100 years later. That discovery confirmed Einstein's vision with ringing clarity. Yet the triumph only deepened the mystery. Quantum mechanics insists that everything at the smallest scale is made of particles and waves that come in discrete units. Energy, spin, and even empty space itself fluctuate in quantum jitter. But general relativity treats spacetime as perfectly smooth. When physicists attempt to apply quantum rules to spacetime geometry, the equations explode into infinities, predicting impossible quantities that break the very logic of mathematics. The two great pillars of physics refuse to merge. This has led to a question that is both humbling and profound. Could it be that gravity is the one theory that is correct at large scales only because it hides a deeper truth underneath? If electrons behave according to quantum rules, and atoms obey quantum rules, and all matter emerges from quantum ingredients, should not the shape of space that holds them also emerge from something? Quantum scientists began to look for cracks in Einstein's picture. They peered into the early universe where spacetime became so small and so dense that its quantum fabric could no longer be ignored. They examined the hearts of black holes where gravity crushes matter so completely that space-time curves toward infinity. These regions are where general relativity breaks and quantum mechanics must take control. And yet, no one could provide a consistent model of what quantum space-time should look like. Then came an unlikely suspect, a concept so simple that it hides beneath almost everything we do. Information. Information is not just letters on a screen. It is the physical difference between one state of the universe and another. It is the bookkeeping of reality. And in the realm of quantum mechanics, information plays by strict rules. It cannot be lost. It cannot vanish into nothing. Even when particles disappear or transform, the information describing them persists in some form. This rule became the starting point for a new view of gravity. If gravity causes matter to fall into a black hole and disappear forever, that seems to destroy information. But physicists discovered that black holes store their information on their outer surface, not inside. The amount of information they contain is proportional to their area, not their volume. This shocking result hinted that the geometry of space might not be what we think. It could be a kind of projection, a three-dimensional illusion encoded by quantum information living on a lower dimensional boundary. What if gravity emerges from the way information arranges itself in space-time? What if the bending of geometry is really the bending of relationships between quantum states? What if mass and energy are merely clues, not causes, of the curvature around them? A new thought began to form. Perhaps the universe is not made of particles floating inside space. Perhaps space itself is made from the threads of quantum information that stitch particles into existence. Entanglement, the eerie connection that allows two particles to share a state even when separated by great distances, may be the secret glue that holds the cosmos together. Gravity may not be a force acting through space. Gravity might be the result of space emerging from quantum information. This idea is bold. It is controversial. And yet it is gaining momentum because every path that leads toward unifying physics seems to point in its direction. As if gravity has been whispering all along that it is not a fundamental actor but a grand illusion arising from a deeper logic of the universe. We stand at the brink of a revolution in understanding. The question is no longer why gravity is so strange, but what hidden structure gives birth to it. The solution might reveal the true architecture of reality. And that architecture may not be made of matter or energy. It may be made of bits. Gravity has always seemed like a simple consequence of mass, an unavoidable attraction written into the structure of nature. Yet the deeper physicists looked, the more gravity appeared not as a basic ingredient, but as a product of something hidden. Think of a fabric that appears smooth from afar, but when examined closely, is revealed to be woven from countless tiny threads. Einstein discovered the fabric. Quantum mechanics has revealed the threads, and information theory is now exposing the invisible loom that arranges them. Quantum information is not a metaphor. It is a concrete mathematical substance that determines what states a system can exist in and how those states can evolve. When two particles become entangled, they are joined by information that treats distance differently from how our intuition treats space. One may be near and the other impossibly far, separated by light years, yet they behave as one. Their properties synchronize in a manner that defies classical physics. The information describing the pair does not reside in either particle alone, but in the connection between them. That connection does not live inside space. It helps create space. Imagine a vast network of entangled particles. If the strength of entanglement between two regions of that network is high, they behave as if they are close together in space. If their entanglement weakens or disappears, they drift apart in the geometry that emerges from those relationships. The very idea of distance becomes a measure of how much quantum information two places share. Space could be a map of connectivity rather than a stage for movement. This concept transforms gravity from a curved landscape into a reflection of something deeper, mass and energy change the pattern of entanglement around them. When information shifts, the emergent geometry shifts. The path objects follow through. That geometry appears curved. What Einstein interpreted as space-time responding to matter might instead be entanglement responding to information flow. The curvature we call gravity becomes a statistical reshaping of the underlying network. It is an idea both elegant and unsettling. It means that the space we inhabit has no independent existence. Remove the quantum information and space unravels. Remove entanglement and distances lose their meaning. The separation between stars and planets, the room between you and the chair beneath you, becomes nothing more than a measure of how much information binds different parts of the universe together. Everything that feels solid and real may be a shadow cast by something more abstract. And this is the source of gravity's rebellious nature. If gravity is not fundamental, then it should not behave like the other forces. It should not be carried by a particle. It should not appear with the same strength everywhere at every scale. Its weakness becomes a clue that it is not truly a force. It is the slack in the informational threads as they adjust toward maximum efficiency. The bending of space-time is the outcome of information trying to organize itself in the most consistent way possible. This perspective also answers a riddle that has haunted physics for many decades. Why does gravity always attract negative charges and positive charges can repel each other? Because electromagnetic force deals with direct interactions between particles. Gravity deals with the geometry that cradles them. There is no opposite to mass because mass is simply whatever distorts the informational structure that creates space. If two masses are present, their distortions overlap. They settle into a configuration that brings their geometry together. Attraction is not a force pulling them. It is the shape they must adopt. If this view is correct, physics is entering a new era. Instead of quantizing gravity directly, scientists may reveal that gravity is the effect of something already quantum at its core. The failure to detect the graviton may not be due to its weakness, but its absence. The graviton would be like searching for the sound of a wave in a web rather than the motion of the web itself. The wave is real, but the thing one tries to identify as the particle might never have existed. To test these ideas, researchers look toward the most extreme objects in the cosmos, black holes. These are places where the rules of the universe buckle. They compress so much mass into such a small region that space-time curves until there is no return. Yet, when physicists calculate the amount of information held inside a black hole, they find something astonishing. The information does not scale with the volume of the black hole. It scales with the area of the sphere surrounding it. The area, not how much space it contains, but how much surface covers it. This is a stunning hint. It suggests that information of a region inside space is stored on a lower dimensional boundary outside that region, almost as if the interior is a projection. If one follows this idea fully, it implies that the three-dimensional world we experience could be an emergent hologram, a vivid three-dimensional reality formed from information imprinted on a two-dimensional surface. Space might not contain information. Information might contain space. So gravity may not only be an emergent effect, gravity may be the clearest sign that we are living inside a universe where information is more fundamental than geometry. The cosmos itself could be a computation that continuously refines its structure. And the laws of physics are simply rules governing how information can change. This realization does not cheapen the universe or reduce it to mere code. It elevates it. Code is not lifeless. Code generates worlds. Code evolves. Code creates meaning through patterns. If reality is a grand informational system, then the stars are modules of a majestic algorithm, and consciousness is an emergent property of a network learning about itself. Yet we must remain rigorous. These ideas are bold and beautiful, but beauty alone is not truth. Experiments must decide. Nature must confirm or reject them. The challenge ahead is immense, but the rewards could reshape our deepest understanding of existence. Gravity has always seemed like the most obvious force. Now it may become the greatest revelation. The clue that tells us the universe is not built on particles alone. It is built on relationships, on the links between entities rather than the entities themselves. Perhaps the true fabric of reality is not space-time. It is information. This is only the beginning. The mystery of gravity invites us to question everything we think we know. And with every question comes the possibility of unlocking a greater truth. In the next chapter, we will explore what quantum information really is, how it behaves, and why it may be the invisible foundation beneath all of physics. Reality has always been described in terms of things: atoms, electrons, stars, galaxies. We imagine the universe as a vast collection of objects placed in a container called space, evolving through something we call time. But quantum mechanics eroded that picture. It revealed that objects are not what they seem. An electron is not a tiny marble orbiting a nucleus. It is a cloud of possibilities, a wave of maybes. It becomes definite only when something observes it, as if existence itself waits for a question before choosing an answer. This strange behavior led physicists to rethink what is truly fundamental. If particles can appear in many states at once and only collapse into one when information about them is acquired, perhaps information is more basic than matter. In the quantum world, information does not simply describe the system. Information is the system. The way possibilities are arranged defines what exists and what does not. To understand this new foundation, imagine a single quantum bit, often called a qubit. A classical bit can be 0 or 1, black or white, on or off. A qubit can be 0, 1, or something in between. It can be both 0 and 1 at the same time, existing in a superposition of possibilities. Only when measured does the qubit pick a definite answer. Before that, it is like a coin spinning through the air, not heads or tails, but both at once. Yet unlike a coin, this is not our ignorance of the outcome. The dual state is a real physical condition that can influence other systems. Now imagine two qubits becoming entangled. This is one of the strangest forms of information ever discovered. When qubits are entangled, their fates become linked so tightly that knowing the outcome for one instantly tells us the outcome for the other, no matter how far apart they are. Quantum mechanics does not allow the information to be localized. The description of the pair lives in the relationship between them. Einstein called it spooky action at a distance, but today we know it is a natural feature of the quantum logic that underlies reality. This is where information becomes physical. Consider a famous experiment that tested this idea. Two particles are created in a single event and fly apart in opposite directions. Their properties are entangled. Scientists measure them separately, and although randomness remains in each individual result, the outcomes correlate every time as if the particles share a hidden script. Yet there is no script stored in either particle. The information is shared, spread out, not residing in space, but defining space. Such experiments forced physicists to accept that quantum information does not care about distance. It weaves the universe together across emptiness. It does not travel. It is already everywhere it needs to be, because the entangled system is one object divided into multiple locations. Space is a stage built after the fact. Information is the cast that defines where the stage must appear. The principle that information is real and physical is known as Landauer's rule. It states that erasing information requires energy and generates heat. Every time a computer deletes a number, a small amount of energy must be spent to remove the stored state. This is not metaphor, it is a measurable act of physics. The universe treats information as something with weight, something with cost, something that cannot simply vanish. This changes everything. If information is physical, then the laws of physics are really laws that govern how information may rearrange itself. Matter becomes a specific type of information storage. Forces become the ways information flows through space. And entropy, the measure of disorder becomes a measure of how much information is hidden from us. Seen this way, the universe resembles a cosmic information processor, not in the trivial sense that it runs like a computer, but in the profound sense that every physical event is an update to the grand register of existence. When a particle decays, information moves. When an atom absorbs a photon, information updates. When stars explode and scatter heavier elements into space, information spreads outward to shape new worlds and new life. But if information is the foundation of reality, what is it made of? Here lies a profound twist. Information is not a substance, it is a pattern of distinctions between possibilities. What separates one universe from another is not the building blocks, but the choices encoded in them. The qubits of the cosmos record every interaction, every cause and effect, every entanglement that binds the world together. And these patterns have structure. Quantum information does not simply float in a void. It forms networks. The nodes are quantum systems. The links are entanglement. This network has no fixed geometry at first. Instead, the geometry we experience emerges when enough quantum information is woven into a stable structure. Space might simply be what it feels like to move across the entanglement network. Time might be what it means for information to change from one moment to the next. There is an astonishing implication. Distance and separation are illusions created by incomplete connectivity. If two regions of the universe share a dense web of entanglement, they appear close. If the entanglement weakens, they drift apart. The fabric of space-time could be a map of information flow, not a pre-existing container. Reality may not be built on matter, but on the relationships that define matter. And what we call gravity might be the most visible reflection of this hidden architecture. Not a force, not a curvature of a passive fabric, but the statistical tendency of information to arrange itself into the most stable structure. Gravity might be the pressure of reality trying to keep its information coherent. This is an idea still in formation. It demands evidence. It demands careful thought. Yet every year more experiments and theories push physics closer to this possibility. The frontier of knowledge is shifting away from particles and fields towards something more abstract and more universal. Understanding quantum information may be the key to unlocking the true nature of the cosmos. Because if information defines what is real, then the universe is not just something we observe, it is something that is constantly answering questions, and those answers build the world around us. In the quantum world, reality does not behave like a set of objects sitting inside space. Instead, it behaves like information flowing between possibilities. Every particle is a question waiting for an answer. Every measurement is the universe speaking. And what we call a fact is simply the outcome that becomes locked into the structure of information. But this raises a deeper question. If information is so fundamental, where is it stored? How does the universe keep track of every detail without losing anything? Are there limits to how much information can exist in one region of space? To answer these questions, physicists study something known as entropy. In ordinary life, entropy is a measure of disorder. A messy room has higher entropy than a tidy one because there are more possible messy states than ordered ones. In the quantum sense, entropy measures how much information about a system is hidden. If one knows everything, entropy is low. If one knows very little, entropy is high. This is not just a statistic. It is an objective feature of the universe. Entropy plays a powerful role in physics. It explains why heat flows from hot objects to cold ones. It explains why certain chemical reactions occur naturally and others do not. It even explains why time seems to move in one direction. The future has more possible states than the past. Information spreads out. Things become more uncertain. Entropy grows. The universe keeps increasing its informational possibilities, like a story that gains more twists with every chapter. Quantum information added a surprising new dimension to entropy. Entanglement creates entropy because measurements performed on part of an entangled system hide information about the whole. Even when everything is perfectly ordered at a global scale, the division into separate subsystems increases the apparent disorder. The invisible relationships carry information that we cannot see. This hidden structure gives rise to what is called entanglement entropy, and it may be the number that tells space how to exist. Picture a pair of qubits that are maximally entangled. One cannot describe either qubit alone. All the certainty exists in the connection between them. Now imagine many qubits forming a network. The entanglement entropy of the regions where the network divides determines how much information passes across that boundary. Physicists learned that the entropy scales with the size of the boundary, not the volume of the region. This discovery did not seem important at first, but later it became one of the most essential clues in modern physics. If information in space scales with area, not volume, then space itself must be a hologram. A hologram is a two-dimensional surface that encodes a three-dimensional image. The picture looks three-dimensional, but the information remains two-dimensional. The universe may work the same way. All the physics we see inside space could be encoded on surfaces that surround it. The inside appears real because our perspective interprets the encoded information as depth. Space could be a projection, a vivid, informational illusion. This idea is known by a name we will explore more deeply soon: the holographic principle. It emerged from the study of black holes, where the logic of quantum information collides with the logic of gravity. And it leads to the shocking possibility that the maximum amount of information any region of space can contain depends not on the amount of space inside, but on the size of its surface. A planet, a star, even this room, all would have informational limits written on their boundaries. This reshapes our understanding of the cosmos. It means that when we move through space, we are interacting with data stored in the geometry around us. The reason we cannot pass through walls may have less to do with solid matter than with incompatible informational patterns. Objects do not resist because they are made of substance. They resist because their informational codes cannot overlap. Quantum information also revealed another astonishing truth. When scientists carefully track the evolution of quantum systems, no information is ever destroyed. Not when atoms collide, not when stars burn, not even when something falls into a black hole. The universe protects its information like a careful accountant who never lets a number disappear. If something seems lost, it is merely translated, scrambled, or relocated. This principle is known as unitarity. It is one of the deepest laws in quantum mechanics, and it conflicts directly with the classical idea that a black hole can swallow information forever. That contradiction created a crisis called the information paradox. How can information survive inside a region where space-time collapses behind a one-way boundary? Could the universe violate its own laws, or is our understanding of space and gravity incomplete? To answer that puzzle, physicists had to take information far more seriously. They discovered that when black holes slowly evaporate by emitting particles known as Hawking radiation, the information that went in must eventually come back out. This means the surface of a black hole acts like a storage device. It records everything that ever falls into it. And as the black hole shrinks, that stored information escapes in extremely subtle quantum correlations. If a black hole can behave like a cosmic hard drive, then information must be the deeper truth. And gravity is merely a side effect of how that information arranges itself. Even Einstein's greatest insight begins to look like the visible shadow of a hidden order. Geometry, curvature, motion, the flow of time, all might emerge from networks of entanglement maintaining consistency across the universe. This transforms our perspective. We are not floating through empty space. We are part of an enormous informational structure weaving itself into reality at every moment. Matter is information with mass. Energy is information capable of movement. Temperature is information scrambling more rapidly, and gravity is information finding the most efficient configuration. So when one looks at the night sky and sees stars glimmering like jewels scattered across a velvet void, one is really witnessing a symphony of information being played out in relationships so intricate that their patterns generate space itself. The distances are not fixed. They are agreements between entangled states. The cosmic web of galaxies may be a tiny reflection of the quantum web beneath everything. The next step is to follow this line of thought into the most mysterious places known to science, black holes. In their depths, the conflict between gravity and quantum information becomes unavoidable. The laws of physics clash, paradoxes arise, and in the fires of that contradiction, physicists have begun forging a new understanding that points to a universe built not of matter, but of meaning. Not of things, but of information. Information is powerful, not because of what it is made of, but because of how it is arranged. Imagine a library with shelves stretching beyond sight. The value of the library does not come from the paper and ink. It comes from the pattern of meaning stored inside those pages. Knowledge is the organization of symbols. The paper is just a vessel. In the same way, the universe may be a library where matter and energy are merely the pages. Quantum information is the story being written. To understand how fundamental this story may be, let us look more closely at how the universe protects information. Consider a proton. It is one of the most stable particles in the universe. Even after trillions upon trillions of years, it remains intact. The reason is not simply luck. It is because the information that defines a proton is deeply encoded in the structure of the universe. If a proton were to decay, that information must go somewhere. It cannot be deleted. Quantum rules demand that the ledger of reality stay balanced at all times. Now consider something even more dramatic. When matter falls into a black hole, classical physics says everything is lost. The black hole hides every detail behind a boundary from which nothing can escape. But quantum mechanics insists that the information must continue to exist in some form. This conflict was ignored for decades because black holes seemed too distant and too extreme to challenge the foundations of physics. But then Stephen Hawking proved that black holes are not entirely black. They emit radiation. Over unimaginable stretches of time, they slowly shrink. This discovery forced a confrontation. If black holes evaporate, what happens to the information trapped inside them? Hawking originally suggested that the information disappears forever, but that would break the very core of quantum mechanics. It would create a flaw in the universe at the most fundamental level. Physicists refused to accept this. A long debate followed, spanning generations, filled with passionate arguments and new ideas that stretched the boundaries of theory. The answer that emerged was astonishing. The information never truly enters the interior of the black hole. Instead, it becomes encoded on the surface. Every bit of matter that falls in increases the area of the black hole by a tiny amount. That area measures how much information is being stored. The surface acts like a vast database. As the black hole evaporates, tiny fragments of that stored information leak out, twisted and scrambled, but not destroyed. This realization flipped the understanding of space inside out. Volume seemed less important. Surfaces became the true guardians of reality. And the rule that the amount of information scales with area rather than volume hinted at an entirely new way to think about the universe. If the deepest places in physics operate this way, perhaps every region of space does too. Perhaps all the information that defines the universe is stored not in the places we see, but on boundaries we do not yet fully understand. There is another lesson hidden here. Entanglement does not just store information, it also limits what can be done with that information. Because when two systems are entangled, the full description of each part depends on the other. If one tries to separate them, one cannot fully describe either alone. The universe appears to be arranged to prevent information from existing in isolation. Relationships are more fundamental than the objects being related. That idea leads to a radical interpretation. Objects may not truly exist on their own. They exist only through the information that connects them to the rest of the universe. A particle without entanglement would have no location, no role, no identity. It would be a silent bit without context. Existence may require connection. This concept echoes through all of physics. Atoms form molecules by sharing electrons. Stars form galaxies by the pull of mutual gravitation. Even life emerges from chemical networks that exchange and process information. From qubits to organisms to cosmic structures, everything grows from relationships. When viewed through this lens, information is not just the foundation of matter, it is the foundation of meaning. There is still a mystery to confront. If information is the basic currency of the universe, who or what keeps the accounts balanced? Who decides how information flows and changes? There must be laws governing the transformation of information through time. These laws are the true laws of physics. They dictate which changes are allowed and which are impossible, and they must operate consistently at every scale, from quantum interactions to the shape of the cosmos. Unitary evolution is the name physicists give to the rule that information is never destroyed. It ensures that the present always contains the seeds of the past. If one could reverse time perfectly, every detail would reappear. Yet we feel time move forward. We see eggs crack, but never uncrack. We watch stars burn and fade, but never reform from cold ash. Entropy grows. The universe gains uncertainty. How can these ideas coexist? The answer lies in perspective. From the viewpoint of the entire universe, no information is lost. From our limited viewpoint inside it, most information is hidden. Entropy increases not because reality forgets, but because we do. The boundaries of our knowledge expand unevenly. Time is the measure of how much we fail to know. Information remains conserved, but its accessibility changes. This leads to a profound insight. Consciousness itself may be tied to information. Our thoughts, memories, and awareness are patterns of information processed inside a complex biological network. The sense of self arises from the organization of that information. When we look at the stars, the information in our minds interacts with the information encoded in photons that traveled across cosmic distances. The universe is not just outside us. It becomes part of us through the flow of information. If the universe is a grand network of entanglement, and space emerges from communication between quantum states, then we are participants in that fabric. We do not merely observe information, we are made of it. The same rules that shape galaxies also shape thoughts. The same entanglement that weaves space-time could be the essence of connection between minds and the cosmos. And so we return to gravity. If gravity is a reflection of how information arranges itself, then understanding quantum information is the first step toward revealing gravity's true nature. The next chapter will bring us to the most extreme environments in the universe. Places where geometry becomes alive and information is pushed to its limits. Black holes will show us why information and gravity are inseparable, and why the universe keeps nothing to itself. Black holes are the most mysterious objects the universe has ever made. They are born in the fiery deaths of giant stars, when gravity overwhelms every other force and collapses a massive core into a region so dense that light itself cannot escape. What remains is a place where space curves upon itself so steeply that all paths lead inward. A place where time slows to a crawl. A place where the known laws of physics bend and strain. For a long time, scientists believed black holes were simple. Once something crossed the invisible boundary surrounding them, known as the event horizon, it would be lost forever. Every detail about what fell in, all its complexities, all its information, would be erased from existence. To the outside world, a black hole could be perfectly described by only 3 numbers: its mass, its electric charge, its spin. Everything else disappeared, as if the universe threw its secrets into a furnace with no smoke and no ashes. This view was elegant. It made the math clean, but it carried a hidden disaster. If information can truly vanish inside a black hole, then quantum mechanics collapses. The universe would lose track of its own accounting. The rule that information is preserved would be broken, and if that rule fails even once, the whole structure of quantum physics might unravel. The paradox stared physicists in the face, unsolved and haunting. Stephen Hawking took the puzzle further. He discovered that black holes are not entirely black. They glow with a faint radiation created by quantum effects near the event horizon. Pairs of virtual particles constantly appear and annihilate in the vacuum of space. Near a black hole, one particle can fall in while the other escapes, stealing a tiny bit of energy. Over unimaginable spans of time, this process slowly shrinks the black hole until nothing remains. But then comes the devastating question: what happens to the information? The radiation Hawking described contains no imprint of the matter that fell in. It is featureless heat. If the black hole disappears and the information does not escape, then it is gone forever. Information destroyed. Quantum mechanics in ruins. This became the information paradox, one of the greatest conflicts in theoretical physics. The two most successful theories ever discovered, quantum mechanics and general relativity, seem to disagree at the edge of a black hole. Physicists could not allow that. They dug deeper. They questioned every assumption. And slowly, the black hole revealed a shocking truth. The information does not go inside. It goes onto the surface. When something falls toward the event horizon, the details about it become imprinted on that boundary, like faint etchings on a cosmic storage device. The interior does not grow more complex. The surface does. This leads to the most astonishing fact black holes have ever taught us. The amount of information a black hole can hold is not proportional to its volume. It is proportional to its area. The surface is the vault of information, not the space inside. This means the interior of a black hole may not be what we think. It may be an emergent illusion, a geometry created from the data encoded on the boundary. And if that is true for black holes, why not for everything? Perhaps all of space works this way. Perhaps the three-dimensional world we experience is a projection of information stored on distant boundaries. This idea became known as the holographic principle. It does not claim the universe is fake. Instead, it reveals that what we see as depth might come from something more primitive and more elegant. Geometry could be information made visible. Black holes are not merely destructive monsters. They are windows into the informational soul of the universe. They demand that we take information seriously, that we treat it as real, as matter, as essential as energy. They show that if information attempts to vanish, the structure of space-time itself steps in to preserve it. Imagine that every atom you consist of, every photon you have ever seen, every memory stored in your mind, every detail of the world around you, is inscribed somewhere in the cosmic ledger. Nothing is lost. Nothing is forgotten. Reality keeps records at the deepest level. Black holes, once symbols of oblivion, have become symbols of perfect memory. And yet, the more we understand them, the stranger they become. If the information is on the surface of a black hole, does the interior truly exist? Or is it a kind of holographic hallucination produced by the boundary data? Could two observers disagree about whether something has crossed the horizon or not? Can space-time itself be different depending on who observes it? Questions like these are now at the frontier of physics. They challenge our assumptions about objectivity and reality. They force us to reconsider what it means for something to exist. The answer seems to be that existence is tied to information. If something is not encoded anywhere, it may not be real. This makes gravity look less like a force and more like a storyteller. It writes the structure of space, so that information always has somewhere to go. It shapes the paths of planets and stars to preserve every detail of the cosmic narrative. When something is hidden behind a horizon, gravity rewrites the world so that the information does not disappear. This changes the way we see the universe. Space is not an empty stage. It is a record of relationships. Every location is defined by the information stored upon it. Distance becomes the difference between knowledge stored here and knowledge stored there. Gravity becomes the map of how that knowledge affects motion. Black holes stand as reminders that physics is not finished. They are the crucible where the old ideas of geometry meet the new ideas of quantum information. They are teaching us that reality may be woven from data more fundamental than space itself. In the next chapter, we will follow this thread further. The holographic principle will expand into a picture of the universe that challenges our intuition at every turn. A universe where the true action happens not in the volume we move through, but on the distant boundaries that define it. The paradox of information in black holes forced physicists to confront a fundamental misunderstanding. They once believed the interior of a black hole was a place, a region of spacetime that existed whether or not anyone could see inside. But quantum information refuses to allow a hidden realm where data can vanish. So physicists began to suspect that the interior might not be fundamental at all. It might be a clever construction that appears only when certain observers describe the universe. Like a mirage, it is real to the one who sees it, yet dependent on a deeper truth. Consider someone falling toward a black hole. They do not feel anything special when crossing the event horizon. There is no wall, no barrier. They simply pass through, unaware that they have entered a region where escape is impossible. To them, the interior exists. But to someone watching from far away, the falling person never crosses the horizon. Instead, they appear to stretch and slow, their information spread thinly across the surface as time itself nearly stops. Both observers are correct, but they cannot agree on the same picture of reality. This is not just philosophy, it is a clue. The nature of existence changes with perspective because existence is not a thing in itself. It is an information structure. The universe does not store one universal description of events. It allows many consistent descriptions to exist, each depending on the available information. Gravity does not create a single objective spacetime. It creates a geometry shaped by knowledge. Black holes sharpen this truth. They are places where gravity pushes information to its limits. As the surface grows, the informational capacity grows. As the surface shrinks, the information must leak back into the universe. This happens through Hawking radiation, which is incredibly subtle. Each particle escaping carries a tiny fragment of the black hole's memory. The information is not lost. It is just unimaginably scrambled. This scrambling is not random chaos. It is a process so perfectly efficient that physicists call black holes the fastest scramblers in nature. Any information that enters a black hole is mixed thoroughly within a short time, making extraction extremely difficult, but not impossible. It is like taking a book and tearing every page into microscopic shreds, then mixing them in the wind. The story is still present, but deciphering it becomes a monumental task. Yet the universe is patient. Even if a black hole lives for 10 to the power of 67 years, that time is finite. When it evaporates completely, every page will eventually be returned to the world, though out of order and nearly unrecognizable. Quantum rules demand this. They keep the book intact even when it seems to have burned to dust. This leads to a shocking thought. If black holes are the most extreme information processors in the universe, maybe they reveal something universal about the fabric of spacetime. Perhaps the entire cosmos behaves like a hologram. Not a false universe, but a universe where the deepest layer is two-dimensional information from which three-dimensional space emerges. To understand this, imagine a hologram card. The shimmering three-dimensional image is not inside the card. It is encoded on the flat surface in complex patterns of light and dark. The third dimension arises only when light interacts with the code. In the holographic view of the universe, the space we walk through works the same way. The distances between stars, the shapes of galaxies, the geometry of space-time itself all appear real because our perceptions interpret the underlying information as depth. We feel space, we experience volume. But the information that defines those experiences may live elsewhere, written on a cosmic boundary far beyond our sight. This idea gained incredible strength from discoveries in theoretical physics, where two very different kinds of theories turned out to describe exactly the same reality. One of these theories has gravity and curved space. The other has no gravity at all and describes particles interacting in a flat realm. When scientists realized these theories were equivalent, a breathtaking conclusion followed. Gravity and space-time might be emergent. They might arise from information living on a boundary with one fewer dimension. This was not speculation. It was a precise mathematical identity. It revealed the possibility that our universe is the inside of a hologram generated by quantum information painted on a distant surface. Black holes were the first hint. They showed that the information content of a region is stored on its boundary. That rule may apply to the entire universe. It means the place we call inside is a projection of data elsewhere. And if this is true, then gravity is not fundamental. It is the shape that information takes when it tries to remain consistent across the projection. It is the story that emerges when bits of quantum data cooperate to form a geometry that feels smooth and real. Another lesson comes from looking at how black holes handle energy. When mass falls toward a black hole, the energy increases the curvature of space-time. But that curvature is really a shift in how the surface stores the information. Mass is information with the power to bend geometry. If the mass changes, the information rearranges itself. Gravity is the universe adjusting its geometry to maintain its informational balance. Black holes also teach us something beautiful about limits. There is a maximum amount of information any region of space can hold. If one tries to store more, the region collapses into a black hole. The cosmos sets a strict rule. There are no infinite libraries, no unlimited data centers. The universe protects itself from overload by transforming excess information into gravity. This limit is known as the Bekenstein bound, and it tells us that the universe has a finite capacity for knowledge. Every cubic centimeter of space has a maximum number of bits that can define it. These limits do not depend on atoms or molecules. They depend on the fundamental constants of nature: the speed of light, the gravitational constant, the quantum of action known as Planck's constant. These constants define the rules of the cosmic information game. So in black holes, we discover the most important lesson yet. Information is not merely something that the universe contains. It is what the universe is. Every horizon is a screen. Every region is a record. Every particle is a bit. Every gravitational curve is a response to informational change. And once we accept this, gravity, the most puzzling force in nature, finally begins to make sense. Its strange weakness, its universality, its deep connection to geometry, all become natural consequences of a reality built from entanglement and encoded on boundaries. We are beginning to see how gravity and information are entangled in a dance that spans the cosmos. In the next part, we will follow how this relationship leads to a radical vision. That space itself may be the result of entanglement. That cutting the informational links severs geometry, and that without quantum information, space-time would fall apart into isolated fragments of nothingness. The deeper physicists studied black holes, the clearer it became that these objects are not exceptions to the laws of physics. They are demonstrations of the universe's most essential rules. One of these rules is that information cannot go missing. Another is that information defines geometry. And when those two principles collide in the heat of a collapsing star, the universe reveals secrets that would otherwise remain invisible. Think again about the event horizon. It is not a physical surface one can touch. It is a place where the flow of time becomes so distorted that escape becomes impossible. But the horizon takes on a second identity. It is the surface on which information is written. As matter falls toward the black hole, its quantum state becomes etched into the horizon with astounding precision. The black hole does not swallow information. It absorbs it onto its boundary. The reason this matters so deeply is that space-time itself cares about information. It curves and twists to protect it. Imagine a blanket stretched tight. Place a marble on the blanket, and the marble sinks, creating a dip. But now imagine that the blanket is not made of fabric. Imagine instead it is made of information. The dip is not caused by weight. It is caused by the amount of information being stored in that region. The blanket curves to hold that information securely. This is how gravity behaves when seen through the lens of black hole physics. The curvature of space-time is the universe making room for information. This idea becomes even more important when one considers the strangest property of black holes. When a black hole shrinks, its surface shrinks. The information stored on it must come out. The escaping Hawking radiation carries that information away bit by bit. The process is incredibly slow, and it converts the black hole into a fountain of scrambled knowledge. This is where physics touches something close to poetry. The most powerful destroyers in the cosmos turn out to be its most faithful librarians. They guard information with their lives, and when they die, they release it back to the universe. But if the information is encoded on the horizon, what does that say about the interior of the black hole? The interior is a place where Einstein's equations suggest a singularity, a point where density and curvature become infinite. But infinities in physics often signal that we are using the wrong description. The singularity may not truly exist. It may be a mathematical illusion created when we insist on treating space-time as fundamental. Perhaps there is no inside in the usual sense. What we perceive as the interior could be a projection of the information stored on the horizon. That projection feels real to someone falling in because they are part of the information being projected. But if no information truly resides inside, then the inside is a useful fiction. A story space-time tells to allow matter to fall without violating quantum rules. This realization changes the very meaning of place. Somewhere and nowhere become matters of perspective. There are no absolute positions. Reality depends on how and where information is being observed. Space becomes a concept that emerges only when information is organized in a particular way. This leads to an even deeper conclusion. If information on a surface can generate a three-dimensional interior, then perhaps the universe we live in is itself the interior of a vast informational surface. We do not know where that surface lies or what it looks like. It could be at the edge of the visible cosmos. It could be something more abstract. But holography suggests that the world around us is not the base layer of reality. It is a derived experience. Black holes gave us this revelation, but their lesson extends far beyond the boundaries of collapsed stars. The entire universe might obey the same rules. Every horizon, from the surface of a black hole to the cosmic horizon that surrounds our view of the universe, may encode information that creates the space-time within. The cosmos could be a tapestry woven from quantum data stored at its unseen edges. If this is correct, then gravity becomes a sign that the tapestry is being tugged. It measures how the threads shift when information moves from one place to another. Gravity may be the smoothing force that prevents tears in the cosmic fabric. It keeps the informational structure coherent so that the illusion of continuous space remains unbroken. There are experiments happening right now to test these ideas, although the task is enormous. Physicists observe how galaxies rotate far from their centers and find motions that gravity, as Einstein described it, cannot explain. Some suspect that this too may arise from the informational basis of gravity. Instead of inventing invisible matter to fix the equations, perhaps the entanglement structure of the universe is behaving in ways we do not yet fully understand. And so black holes guide us toward the next step. If gravity emerges from information on a boundary, then what creates that information in the first place? The answer may lie in quantum entanglement. The links between particles could form the scaffolding of spacetime. If entanglement creates geometry, then gravity becomes the elasticity of that geometry. It is the natural response of the network when connections stretch or compress. Cut the entanglement, and space tears apart. Increase it, and space becomes tightly bound. Gravity would simply be the shadow cast by the ever-changing dance of quantum information. This is the bridge that leads to a new understanding of reality, a universe where space is not the stage, but the cast, where distance is defined by relationships, where gravity is the consequence of information keeping itself consistent. As we step into the next chapter, we will explore how these daring ideas become a fully developed principle. The holographic universe suggests that all of reality is encoded on surfaces. Now we will see how those surfaces might work, and how entanglement could be the architect of the very world we experience. Imagine standing on the shore of a quiet lake at night. The water is perfectly still, reflecting the moon and the stars above. The reflection appears almost as real as the sky itself. The shimmering moonlight stretches across the surface, creating an image that looks deep and full of space. Yet everyone knows the truth. The depth is an illusion. It is a trick produced by light and perception. There is no sky inside the water. There is only a flat surface encoding a three-dimensional scene. Now imagine that the universe is the lake, and the space we move through every day is the reflection. This idea is one of the most extraordinary shifts in scientific understanding to ever emerge from physics. It suggests that everything we know, stars, planets, cities, the room around you, and even your body, might be the three-dimensional image of information stored somewhere else. Not in a faraway place one could travel to, but on a boundary that defines the universe itself. The world that feels so spacious and volumetric may in fact be the product of a deeper layer of information living in fewer dimensions. This concept is known as the holographic principle. It began as a wild conjecture, a daring attempt to solve the black hole information paradox. But it has grown into a powerful framework supported by mathematics so rigorous that scientists now believe it may be the correct description of reality. It proposes that what we think of as physical space emerges from quantum information encoded on a surface that has one less dimension. In simple terms, the universe we see may be a hologram, not a fake universe, not a simulation in the ordinary sense. A physical hologram where the real data is stored on a boundary. The volume we experience is the interpretation of that data. Just as a hologram on a credit card contains a three-dimensional image within a two-dimensional pattern of light, the cosmos may contain a three-dimensional world encoded in a two-dimensional structure at its edge. The key to this revolution was found in a surprising place: a universe with a strange shape known as anti-de Sitter space. This is a space-time that curves in a way unlike our own. It is like a bowl with walls that curve outward infinitely. On the boundary of this world sits a quantum system without gravity. Inside the bowl, gravity behaves just like it does in Einstein's theory. Two completely different descriptions, one with particles interacting in flat space, one with curved space-time and gravitation, yet they are exactly the same. This discovery was made in 1997 by a physicist named Juan Maldacena. He demonstrated that the physics happening on the boundary is identical to the physics happening inside. Every event that occurs in the volume has a perfect translation into information on the surface. Every quantum fluctuation on the surface generates a change in the geometry inside. Two languages, one reality. Gravity does not vanish, it emerges. This was not a vague philosophical suggestion. It was a precise mathematical identity known by the abbreviation ADS-CFT. It means that a theory with gravity in a curved spacetime is equivalent to a theory without gravity living entirely on the boundary of that spacetime. Gravity appears only in the emergent three-dimensional picture. The fundamental physics lives on the surface. This realization sent shockwaves across theoretical physics. It revealed that space might not be fundamental. Space-time might be a secondary effect, a convenience, a useful way to talk about physics at low energies and large scales. But far beneath the surface, a richer structure governs existence, a structure made of quantum fields and entanglement, not geometry. One can imagine the boundary theory as a gigantic sheet of information. Patterns unfold across it like ripples. Those patterns encode the positions of stars, the energies of particles, and even the passage of time. If one zooms in on the boundary, the geometric illusion disappears. What remains are bits of information in a quantum dance. The universe inside is a story those bits tell. This changes how we think about distance. When 2 points in the universe appear close together, it means their information is tightly linked on the boundary. When they seem far apart, it means the links are stretched or sparse. Geometry becomes a way of describing the strength of information relationships. The shape of space is dictated by how information is organized. The most important part of the holographic principle is that it finally unites what gravity once kept separate. Quantum mechanics and general relativity no longer fight. They become two perspectives of the same truth. One view sees particles and entanglement. The other sees curved space-time and gravity. Both are valid. Both are necessary. But one is deeper. The quantum boundary is the original script. The gravitational interior is the performance. This raises an exhilarating possibility. If the universe generates itself from a lower dimensional information code, then studying that code might allow us to understand everything from the birth of the cosmos to the nature of dark energy and dark matter. The cosmic mysteries that have defied physicists for generations may finally become solvable once space is recognized as the projection that it truly is. The holographic principle also gives us new ways to imagine our existence. We are not trapped inside a box called spacetime. We are part of a dynamic informational network that creates spacetime as needed. Our atoms are not dots on a grid. They are patterns in the boundary code. Our memories and choices are not separate from the physics of the universe. They are expressions of the same information that forms galaxies. This does not diminish our reality. It enriches it. A hologram is not fake. It is a different way of representing truth. Our universe might be more like a masterpiece of computation than a collection of objects. And gravity may be the artistry that gives the masterpiece depth. In the next part, we will follow how this holographic idea leads to an even more radical insight, that the thing giving birth to space is not mass or energy at all. It is entanglement, the invisible threads of information linking particles together. Cut those threads, and the universe fractures. Strengthen them, and space-time becomes smooth and continuous. Gravity may be the gentle pull of entanglement trying to keep the universe whole. The holographic principle suggests that the universe we inhabit is not the deepest layer of reality. Instead, our three-dimensional world is constructed from information arranged in a lower dimensional form. But how does that information build a universe that feels rich and continuous? How does the code become the cosmos? The answer lies in one of the strangest features of quantum mechanics: entanglement. Entanglement is a kind of connection that does not depend on distance or location. When two quantum systems are entangled, their properties are linked so completely that measuring one determines the state of the other, even if they are separated by billions of kilometers. The information describing the pair is not in either object, but in the relationship between them. Now imagine not just two systems, but countless systems, a web of quantum connections spanning the universe. If the strength of those entanglement links determines how close two regions appear, then space itself becomes a map of entanglement. Distance is not measured in meters or kilometers. It is measured in correlation. If two places share a great deal of entanglement, they are near. If their link is weak, they are far. This idea was explored deeply by physicist Mark van Ramsdonk in the year 2010. He asked a bold question. What happens if one takes two regions of spacetime and reduces the entanglement between them? Would the regions simply drift apart, or would spacetime itself begin to tear? He ran the calculations using the holographic duality. The result was astonishing. Removing entanglement breaks the geometry. The smooth fabric of spacetime rips. The interior collapses. Space disappears. The implication was crystal clear. Entanglement is the glue of spacetime. Without it, the universe would fragment into lonely islands of existence. No path, no structure, no gravity. Spacetime is not the stage. It is the product of connectivity. Space emerges when quantum systems share enough entanglement to form a continuous geometry. This realization transformed the understanding of gravity. If space itself is born from entanglement, then changes in entanglement must give rise to curvature. And curvature is what we call gravity. Instead of a field or a fundamental force, gravity becomes the tendency of entanglement to shape the geometry in which particles travel. When mass alters the information structure around it, entanglement responds by adjusting distances. The result appears as an attractive pull. This turns Einstein's picture inside out. Rather than matter telling spacetime how to curve, matter tells information how to arrange its links. The entanglement rearranges, and the curved geometry appears as a side effect. Gravity becomes a visible signal of invisible information, trying to maintain coherence. There is another insight that pushes this picture even further. Quantum error correction. When scientists design quantum computers, they must protect information from noise. They do this by encoding it in a way that allows the system to recover from errors using redundancy built into the entanglement network. The mathematics of this protection looks very similar to the mathematics of holography. In fact, researchers discovered something shocking. The geometry of a holographic spacetime behaves exactly like a quantum error correcting code. This means that the universe protects its information the same way a quantum computer protects data from corruption. Gravity becomes the mechanism that ensures no information is lost when parts of spacetime are disturbed. It smooths out irregularities. It keeps the geometry stable. It ensures survival of the code. Think about that. The stability of the universe may be the direct result of an enormous quantum computation running in the background of reality. When a star bends the space around it, that curvature could be a repair process, redistributing entanglement so the information does not unravel. Gravity might be the universe constantly correcting itself to prevent spacetime from falling into chaos. But if gravity is an emergent effect of entanglement, then what about time? Time has always been the most mysterious dimension. In equations, time behaves differently from space. It has a direction. It flows. It separates the past, which is fixed, from the future, which is uncertain. Yet if space emerges from entanglement, then perhaps time emerges from changes in entanglement. When information evolves, when quantum links rearrange, when correlations shift from one configuration to the next, we interpret that change as time. Instead of time causing change, change causes time. The arrow of time is the growth of entanglement. The expansion of the universe might be the expansion of informational connectivity. The future may be a region of higher correlation than the past. And here lies a connection to entropy. Entropy measures how much information is hidden. As entanglement spreads, the number of hidden correlations increases. Entropy grows. Time moves forward. The intimate link between information, entropy, and time becomes a natural result of entanglement shaping the universe. The holographic principle also offers a profound perspective on our perception of reality. The world feels continuous and smooth, but if one looked closely enough, one might find that the smoothness is an illusion created by an enormous number of entanglement links overlapping. The The scale at which this network becomes apparent may be far smaller than any technology has yet achieved. But the signs are there in the math. Space is pixelated by information, not in a rigid grid, but in a dynamic network that adapts to the state of the universe. This idea does not threaten the reality we experience. It deepens it. We are not shadows on a wall. We are participants in the weaving of space-time. Our presence alters the entanglement network. Our knowledge changes geometry. Consciousness might itself be an emergent phenomenon of this quantum architecture. So when we look up at the night sky and see stars scattered across vast distances, what we are truly seeing are nodes in a grand informational web. The darkness between them is not emptiness. It is structure. The points of light glow because the entanglement network supports stable patterns of energy, and the curvature that binds stars into galaxies is the same entanglement adjusting its bonds to maintain order. This vision is daring. It challenges the common-sense picture of a universe built from objects in space. It suggests instead that objects and space arise together from information. They cannot be separated because they are two sides of the same phenomenon. Geometry is the shape that information takes when it becomes physical. The more we explore this idea, the more gravity appears not as an enigma, but as a masterpiece. It is the whisper of quantum information spreading across the boundary of the universe. The great arc of a planet around a star, the swirling of galaxies, the dance of cosmic structure, all may be the result of information holding the universe together with invisible threads. In the next part, we will follow this idea to its conclusion. If space and gravity emerge from entanglement, then what supports that entanglement? What governs its behavior? And could this explain the mysteries that still confuse us, like the missing mass of galaxies and the unseen energy stretching the cosmos apart? Gravity may be a clue to a deeper structure, just waiting to be uncovered. The holographic universe is not just a mathematical curiosity. It suggests something far more radical, that the truest form of reality exists not inside space, but on the boundaries that define space. The objects and structures we see might be like the images in a dream. They feel real because the information that creates them is arranged in a way that our minds interpret as solidity and distance. But underneath is a deeper architecture built entirely from quantum information. To appreciate how bold this idea is, imagine taking 2 points in space and slowly weakening the entanglement between them. If one could truly do this, those two locations would drift apart in the geometry of space-time until eventually they would become infinitely distant. There would be no path connecting them. Space itself would have been severed. This shows that distances are not measured by rulers or light years, but by the strength of information shared between systems. Place emerges from connection. This also means that if entanglement is increased, space becomes more tightly woven. Objects can approach each other not because they physically move, but because their informational links grow stronger. Space-time adjusts to match these changes. Gravity becomes a measure of how information flows through this network. When matter shifts, entanglement shifts. The geometry reshapes. Planets orbit stars not because of a force pulling them, but because the informational structure guides their path. In this view, gravity is not mysterious. It is the universe relaxing into a state of maximal entanglement. When matter tries to clump, the network adjusts so that information remains as evenly distributed as possible. The graceful arcs of celestial motion are the simplest solutions to the demands of information. The same reason water finds the lowest valley, entanglement finds the smoothest geometry. But if space is a holographic construction, what creates the hologram? The answer lies on the boundary. The surface that encodes everything inside does not sit at some physical edge we could touch. It exists as the limit of what we can ever observe. The cosmic horizon marks the farthest distance from which light has reached us. Beyond it lies information that has not yet entered, our visible universe. The horizon may be where the true coding of space-time lives. Even more surprising is the idea that each observer might have their own holographic boundary. Reality could depend on perspective, because each observer has access to a different set of information. For someone falling into a black hole, space-time continues smoothly inward. For someone watching from afar, the surface holds all the information. Both descriptions are correct, because they are each constructed from the information available to the observer. Truth becomes relational. This is not chaos, it is precision. The universe allows many ways to encode the same information. This flexibility is the reason quantum mechanics and gravity can coexist without contradiction. Entanglement ensures that even when descriptions differ, they always agree on what can be observed. Yet some of the biggest questions in physics remain. Why do galaxies spin faster than they should if gravity works the way Einstein described it? Why does the universe expand at an accelerating rate? These mysteries have long been blamed on invisible forms of matter and energy, dark matter and dark energy. But what if the problem is not missing substances? What if the geometry is behaving differently because the information has been arranged differently? Some researchers believe that the missing mass in galaxies could be an illusion created by the entanglement structure of the holographic universe. If gravity emerges from information, then changes in that information at large scales could create effects that mimic unseen matter. The universe might not be hiding mass. It might be revealing that gravity is not a force we have fully understood. The holographic idea also gives us a powerful way to think about quantum gravity. Instead of forcing gravity into the quantum framework, gravity arises naturally because space-time is built from quantum mechanics at its core. The graviton, the hypothetical particle of gravity, may never be directly found because it might not be fundamental at all. It could be as secondary as waves on the surface of an ocean, useful for describing movement, but not the essence of the water itself. If this is true, then the deepest questions about existence become questions about information. How is it encoded? How does it evolve? How does it generate the structures we see? These are the questions that may finally reveal the truth about the universe. There is one more astonishing possibility. If our universe is a hologram, then space and time could be emergent illusions from a system that might not itself exist in space or time. The boundary could be something far more abstract than a physical surface. It could be the pure mathematics of quantum interactions, a realm where information exists without location, until location emerges as a consequence of correlation. This gives an entirely new meaning to the phrase physics at its foundation. The foundation is not particles or fields, or even space-time. The foundation is information. And everything else arises from the way that information interlocks. As we conclude this chapter, one thing is clear. The universe is more than what we see. Behind every object, beneath every motion, inside every atom, there is a hidden structure of entanglement weaving reality together. Gravity is the shadow of that structure. Space-time is its form. And black holes are the places where the structure reveals itself most clearly. In the next chapter, we will explore what happens when that entanglement changes, when information moves, when the universe adjusts its geometry. We will see how gravity can be interpreted not as a fundamental interaction, but as an entropic effect, a force that arises from the universe striving toward the most likely arrangement of its information. There is a moment in the story of physics when the universe begins to look less like a place and more like a process. A moment when the familiar stage of space-time, once believed to be the container of everything, reveals itself to be the result of something deeper. That moment happens when one looks closely at quantum entanglement, not as a curiosity or a mathematical trick, but as the true source of the geometry that shapes our world. To understand how space-time can emerge from entanglement, imagine the universe not as a single smooth object, but as an intricate web of quantum relationships. Every particle is a node. Every entanglement is a connection. This web has no distance at first, no directions, no dimension. It is a raw network of information, featureless yet full of potential. What turns possibility into place is how these connections are organized. Where entanglement is strong, nodes behave as if they are near. Where entanglement is weak, they behave as if they are far apart. Space becomes a reflection of correlation. This idea contains enormous power. It removes the need to treat spacetime as something pre-existing. Instead, it becomes a consequence of how the universe stores information. Entanglement decides which events can influence each other quickly and which can only interact after long chains of correlation. That influence defines motion. That motion defines geometry. And that geometry is what Einstein called spacetime. The first glimpse of this came from studies of holography. In the strange curved universe of anti-de Sitter space, physicists discovered that the geometry inside responds to the pattern of entanglement on the boundary. Increase the entanglement between two boundary regions, and the interior tightens the distance between them. Cut the entanglement, and the interior stretches or tears. The space within bends to match the shape of information at the edge. Spacetime is not telling matter what to do. Information is telling spacetime how to exist. One can think of entanglement as the invisible architecture of the cosmos. Take away the architecture and the building collapses. The same is true for space. Remove entanglement and space falls apart into isolated fragments that cannot communicate. There would be no paths from one point to another, no distance, no shape. The universe would become a fractured mosaic of disconnected quantum pieces. Without entanglement, there is no space-time. This idea did not arise from imagination alone. It came from detailed studies showing that the mathematical description of entanglement entropy has the exact properties needed to generate the geometry of a continuous universe. Entanglement entropy measures how much information is shared between two regions of a system. In holographic scenarios, that entropy is proportional to the area of certain surfaces inside the space. Those surfaces behave like slices of spacetime itself. The amount of entanglement literally draws the shape of the world. To see why geometry emerges from quantum information, imagine a large tapestry woven from countless threads. From a distance, the tapestry forms a clear image: a mountain, a tree, a star. But up close, one sees only individual threads crossing and connecting. The beauty of the image is not in the thread itself, but in how the threads are arranged. Spacetime is the image. Entanglement is the weaving. Einstein described gravity as the curvature of spacetime. Objects follow the bends in the geometric fabric. They move along the paths that require the least change in their motion. But if spacetime is an emergent structure, then gravity must also be emergent. It must arise from the way entanglement shifts when mass or energy changes the network. Heavily entangled regions create deep wells in the geometry. Objects roll toward those wells not because a force pulls them, but because the geometry guides them. Gravity becomes a shadow cast by entanglement. There is a simple insight that helps this idea make sense. Information likes to be connected. The universe tends to organize itself into states that maximize entanglement. These states are more stable and more natural. They spread influence widely rather than concentrate it. When matter clumps together, it disrupts the smooth distribution of entanglement. The network responds by adjusting the geometry so that the disruption is minimized. We feel that adjustment as gravitational attraction. This picture also explains why gravity is universal. Every form of energy contributes to entanglement. Light, electrons, protons, entire galaxies. Because everything participates in the network, everything participates in the geometry that arises from it. Gravity has no opposites because there is no opposite to information. There is only more or less connection. Where information is concentrated, the geometry curves inward. Where it is sparse, the geometry expands outward. Attempts to detect a particle of gravity, the graviton, have so far found nothing. If gravitons exist, they must interact incredibly weakly. But if gravity is not a force in the usual sense, maybe we should not look for a particle at all. The graviton would be like trying to identify a single thread that causes the entire tapestry to display a picture. The picture is not in one thread. It is in all of them together. Gravity is not one thing. It is the collective behavior of the entanglement network. The connection between entanglement and geometry becomes even more powerful when one looks into the mathematics that governs quantum error correction. In a quantum system, errors can occur when information becomes disrupted by noise. To correct them, one encodes the information redundantly so that the system can recover it, even if part of the data is lost. The rules for this kind of protection turn out to be the same rules used to describe emergent spacetime in holography. Spacetime behaves like a self-healing code. Gravity is the mechanism that repairs errors by reshaping the geometry. This means something astonishing. The stability of the universe may not be a coincidence. It may be a requirement of the quantum code that generates spacetime. The reason planets do not drift apart without cause is that the network would lose coherence if connections weaken too much. The reason black holes form when too much mass is packed into one region is that the code reaches its limit and must rewrite the geometry to preserve information. The rules of gravity could be the rules of survival for the cosmic information structure. Time, too, may arise from the same source. When entanglement evolves, when correlations shift from one pattern to another, the universe interprets that change as time. The direction of time, always pushing forward, always increasing entropy, is the record of information spreading across the network. The arrow of time is the arrow of entanglement. The growth of complexity is the heartbeat of reality. There is also a human meaning buried within this theory. Existence requires connection. A quantum system without entanglement does not have a defined place in space-time. It floats without context. In the same way, a person without connection to others drifts without grounding. Our relationships shape our lives, just as entanglement shapes the universe. The idea that reality arises from connection is not just physics. It is a truth that echoes through every scale of existence. If space-time is built from entanglement, we must rethink the meaning of the universe. We do not inhabit a container. We participate in a network. We are not separate from the cosmos. We are threads woven into its fabric. Every movement, every thought, every interaction reshapes the network ever so slightly. Gravity is the language of those changes. It is the geometry that emerges so the story can continue. So what does this mean for the future of physics? It means that unifying quantum mechanics and general relativity may not require forcing gravity into the quantum mold. It may require acknowledging that gravity was never fundamental at all. It may require recognizing that the universe itself is a quantum state. That spacetime is the emergent stage created when that state becomes large and intricate enough to support complexity. This view brings us closer to answering the greatest question of all. What is the universe truly made of? Not matter, not energy, not spacetime. Those are the visible products of something deeper. The universe is made of information, and spacetime is the theater where that information performs its endless dance. Gravity is not the force that holds us down. It is the connection that holds existence together. There comes a point when a mystery becomes so stubborn that the only way forward is to change the question. Gravity has resisted every attempt to be understood as a fundamental force. It does not fit the quantum mold. It is far too weak compared to the others. It smooths over the universe with gentle insistence rather than sharp precision. Perhaps the problem is that we keep asking what gravity is. The better question might be why gravity happens at all. To discover the why, physicists turn to the concept of entropy. Entropy is the measure of how many ways a system can arrange itself without changing its overall state. In common language, entropy is disorder. A shuffled deck of cards has higher entropy than a perfectly ordered one. A warm cup of tea left on a table will always cool because the heat spreads into the room, increasing entropy. Nature prefers the arrangement that can exist in more possible configurations. Entropy is the universe seeking freedom. Now consider gravity. When planets form, dust and rock collapse inward. When stars form, gas clouds gather into tighter shapes. Gravity appears to create order. It clumps matter into neat structures. That seems opposite to entropy, but look closer. The gravitational collapse of matter releases heat and radiation into space. That heat spreads out. The total entropy of the universe increases. Gravity is not fighting entropy. It is amplifying it on a grander scale. This insight led to a provocative proposal by physicist Eric Verlinde in the year 2011 and later refined in 2016. He suggested that gravity might not be a fundamental interaction. Instead, it could be an entropic effect, a statistical phenomenon created by the universe, maximizing its information storage capacity. When matter shifts, information rearranges. Gravity is the push that emerges from that rearrangement. Imagine a particle moving near a region filled with quantum information. The particle disturbs that information. The system reacts by trying to restore the arrangement that maximizes entropy. The particle feels a pull toward that region, not because a force is acting on it, but because the universe is always trying to reach the state with the most possible configurations. Gravity is the result of this attempt. This picture becomes clearer with something called the holographic screen. It is not a real screen, but a conceptual surface that stores information about the particles inside. When a particle moves, the number of possible configurations on the screen changes. To restore the maximum entropy, the particle is nudged back toward its original location. That nudge is what we call gravitational attraction. This idea turns our understanding inside out. Gravity becomes the universe trying to forget unnecessary information. It is the fading of details, the smoothing of complexity, the erasure of distinctions that no longer matter. As entropy increases, the universe relaxes into simpler macroscopic patterns. Stars and galaxies form because that is the most statistically natural way for matter to behave in a universe filled with information-seeking freedom. Entropic gravity also explains something that has puzzled astronomers for decades. When we look at the rotation of galaxies, the outer stars move faster than they should. According to Einstein, they should drift away into the void. Instead, they stay tightly bound. Scientists proposed invisible matter, dark matter, to explain this. But what if the strange behavior is not caused by unseen mass? What if it is caused by unseen information? Verlinde's calculations show that when one accounts for the information content of spacetime itself, the additional gravitational effect appears naturally. No new matter required. The entanglement of the quantum vacuum contributes to the geometry. Gravity strengthens where information density is high. The outer regions of galaxies are rich with subtle information connections, creating a gravitational pull stronger than expected. The mysterious dark matter might not be matter at all. It could be the shadow of entanglement. This idea does not solve every problem. Some galaxies and clusters still behave in ways the entropic model struggles to reproduce. But the fact that a theory built from information can so closely mimic the effects of invisible matter is astonishing. It suggests that the solution to cosmic mysteries may not lie in particles hiding in the dark, but in information weaving through the light. Entropic gravity also connects beautifully with the holographic principle. If spacetime is a projection of information encoded on a boundary, then entropy is the measure of how much information that boundary holds. When something changes inside, the information on the boundary shifts. The geometry adjusts. We feel that adjustment as gravity. The pull of the Earth on an apple may be nothing more than the apple disturbing the information that defines the space around it. There is something poetic in this. Gravity, the force that shapes stars and galaxies, that guides planets in their dance, that holds oceans fast to a spinning world, might be the quiet pressure of information seeking harmony. The universe is not held together by invisible strings. It is held together by the mathematics of possibility. This picture makes sense of gravity's strange weakness too. Entropy is a subtle influence. It works through overwhelming numbers, not individual strength. The electromagnetic force is powerful because a single photon can push an electron decisively. Gravity emerges only from the collective adjustment of vast networks of information. It is the soft voice of the universe, gentle but irresistible. The entropic idea also suggests that gravity may not act at extremely small scales. If spacetime emerges only when there is enough entanglement to create a smooth geometry, then at the smallest distances, the geometry may not exist in the way we expect. Experiments searching for deviations from Newton's law at tiny scales may reveal the threshold where gravity stops being meaningful. Space itself may dissolve into pure information. We are left with a vision of the universe where information is not just descriptive, it is generative. Entanglement designs the architecture. Entropy drives the motion. Gravity is the consequence. The apple falling from the tree is a piece of information finding its place in the universal pattern. The orbit of the moon is a cycle of entropy-seeking balance. Even the growth of cosmic structure is the spread of information creating order through disorder. And yet, skeptics ask the right questions. How exactly does information rearrangement translate into the precise motions we observe? How does one convert entropy gradients into geometry with all the elegance of Einstein's equations? The answers are emerging, but remain incomplete. Entropic gravity is young. It challenges centuries of intuition. It dares to say that one of nature's most deeply felt forces might be an illusion born of deeper laws. But every great shift in physics began with a daring idea. Newton turned falling apples into universal attraction. Einstein turned gravity into curved space-time. Now a new generation is turning gravity into information. Each step brought us closer to seeing the universe not as a static machine, but as a dynamic computation, a self-organizing system that evolves according to the rules of quantum logic. If entropic gravity is right, the final truth is simpler and more profound than anyone imagined. The universe does not need a force to hold it together. It needs only a system that refuses to forget. Information is immortal. Entropy is inevitable. Gravity is the shape those truths take when they become visible. And so we arrive at a revelation that feels both unsettling and thrilling. The force that bends light and stirs galaxies may be nothing more than the universe keeping track of itself. We are lifted from the surface of Earth not by an invisible hand, but by the deep mathematics of memory. The journey ahead will require new experiments, new ideas, and new ways of thinking. But already the path is visible. It leads toward a cosmos where information is reality, where connection is gravity, and where the search for understanding becomes the search for the source code of existence. Theories can dazzle the mind, but nature has the final authority. For every bold idea in physics, the ultimate test is experiment. Gravity has whispered for more than 100 years that it does not belong among the other forces. Now physicists are finally building the tools to ask the universe whether gravity is truly a child of quantum information. The answers are beginning to appear, faint but unmistakable, at the edges of what we can observe. The first line of evidence comes from the vast rotation of galaxies. For decades, astronomers noticed a strange pattern. The stars on the outskirts of a spiral galaxy move far too quickly. If gravity came only from the visible matter, those stars should fling outward into the dark. Instead, they remain locked in their orbits. To solve this, scientists propose dark matter, an invisible substance that outweighs normal matter by a factor of about 5 and holds galaxies together. It was a clever idea and became the dominant explanation, but no one has ever seen dark matter directly. It leaves no trace except through gravitational effects. After many decades of searching with detectors buried deep underground, with satellites watching cosmic rays, and with particle accelerators smashing protons together, the darkness remains quiet. If dark matter were made of particles, it should reveal itself eventually. But what if the missing mass is not a thing at all? What if gravity behaves differently when the entanglement structure of spacetime extends beyond the visible matter in galaxies? Eric Verlinder's entropic interpretation predicted that deviations from Newton's law would appear precisely where dark matter seems necessary. When astrophysicists compared these predictions to observations of many galaxies, they found that much of the unexplained motion matches naturally. No new particles, no exotic substances, only gravity emerging from the information of space-time. Not every galaxy agrees perfectly. Some appear to demand more entanglement than the theory provides. Others fit beautifully. The struggle continues, but the important shift is that experiments now compare not just matter against matter, but matter against information. That is a profound transformation in how we question the universe. The second line of evidence comes from the behavior of gravity at extremely small scales. If space-time emerges from entanglement, then there must be a threshold below which geometry dissolves into pure quantum information. At very short distances, gravity should weaken or behave unpredictably, because there is not enough entanglement to create a smooth space-time. Researchers have built exquisitely sensitive instruments using tiny slabs of metal suspended on near-frictionless supports. These devices measure the attraction between objects separated by distances thinner than a human hair. Early results suggest slight deviations from the classical prediction, too subtle to claim discovery, but too intriguing to ignore. The possibility remains open that at the smallest scales, gravity begins to fade. A third frontier lies in quantum technology itself. If gravity emerges from entanglement, perhaps entanglement can generate gravitational behavior that can be measured without stars or planets. Physicists are attempting to place two small quantum objects in a state where their gravitational attraction could entangle them. This is an astonishing goal. If successful, it will prove that gravity must obey quantum rules. One does not need a graviton to achieve it. One only needs gravity to create entanglement. The experiment is delicate beyond belief. The masses are so tiny that the gravitational pull between them is far weaker than the faintest electrical disturbance. They must be isolated from every vibration, every stray force, every whisper of the environment. Yet the challenge is being met step by step. Several laboratories have proposed designs. Some predict a result within the coming decade. If those tiny objects become entangled through gravity, it will be the first direct evidence that the geometry of spacetime is written in quantum information. Another remarkable development comes from the study of gravitational waves. These ripples in spacetime are created when massive objects like black holes collide. Detectors on Earth have already observed several such events, confirming Einstein's prediction with breathtaking power. But some researchers believe that subtle patterns in those waves could reveal additional structure. If spacetime is not perfectly smooth but woven from entanglement, gravitational waves might carry faint signatures of that weaving. The search for those signatures has begun. It is like listening for the quietest tremble in a chorus of giants. Yet even giants are made of threads. Beyond observation, physicists are now asking whether the holographic nature of spacetime can be recreated in the laboratory. The answer is yes, at least in a limited form. Quantum simulators allow scientists to design tiny universes on chips of superconducting circuits or arrays of trapped atoms. These devices can encode information in ways that resemble holographic dualities. When they evolve, the behavior inside the simulated space follows patterns similar to gravity. In one groundbreaking experiment, researchers created a configuration that behaved like a tiny wormhole. A particle encoded on one side disappeared and reappeared on the other in a manner consistent with how information might traverse a space-time bridge. This was not a literal tear in the geometry of the universe, but it showed that the mathematics of holography can be physically realized. It proved that emergent geometry is not only possible, but buildable. On cosmic scales, The holographic principle suggests that the edge of the observable universe encodes the physics within. Experiments in cosmology are searching for the imprint of information storage on the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in that background map could reveal how space-time first emerged when the universe was unimaginably young. If entanglement built the early universe, the sky itself holds the fossil record. Even the study of black hole evaporation is no longer purely theoretical. Laws governing the return of information through Hawking radiation are now analyzed with advanced quantum computing techniques. Artificial intelligence and quantum processors are beginning to decode the patterns through which information escapes. These are toy black holes in mathematics, but the logic matches the deepest predictions. If information escapes in a way consistent with the entanglement structure of the horizon, we may someday watch a real black hole reveal its secrets bit by bit. Every experiment so far exists at the boundary of what is currently possible. Some offer hints, others give tension. All demand patience. The universe rarely surrenders its answers quickly. What matters is that the path has changed. Gravity is no longer tested only as a classical force. It is tested as a message from information. The questions now being asked are bold. Does gravity fail inside a quantum computer? Does space-time vanish in systems too simple to store enough entanglement? Can two particles feel each other's presence through the geometry their information creates? Tests like these would have sounded like science fiction only a generation ago. Now they are real proposals with real equipment built by human hands. Still, caution remains essential. Entropic explanations cannot yet match every gravitational observation with perfect accuracy. Quantum entanglement experiments are at the edge of feasibility. The holographic approach applies cleanest to universes unlike our own. But progress does not demand perfection. It demands direction. And for the first time, that direction points not toward new particles or hidden forces, but toward the heart of information itself. The ancient belief was that gravity is the most natural and obvious force in existence. Now it is becoming the most subtle and surprising. The path forward will be shaped by engineers and observers as much as by theorists. Astronomers scanning distant galaxies, physicists listening to the quiet tremble of space-time, quantum scientists entangling tiny spheres in vacuums colder than outer space. All of them are asking the same question. Does information give birth to gravity, or does gravity give birth to information? The emerging answer is that the universe may not separate the two. They rise together, two faces of the same truth. In the next chapter, we will leave the realm of telescopes and accelerators and step into the domain where information is controlled directly. Quantum computers offer the first chance to manipulate the very substance from which space-time might emerge. If the universe is holographic, then even a small quantum system could hold within it the blueprint of geometry. We may soon build not just simulations of gravity, but elements of space-time itself. A quantum computer does not look like a universe. It sits inside a laboratory, often chilled to a temperature near absolute zero to keep fragile quantum states alive. Wires hang like metallic vines. Shielding blocks the noisy outside world. At first glance, nothing about this machine resembles stars, planets, or galaxies. Yet many physicists believe that inside these devices lies the key to space-time itself. If the universe is built from quantum information, then a quantum computer is a tiny version of the same principle. It allows us to shape information directly, to twist entanglement into new forms, and perhaps to watch space emerge in miniature. To understand what might happen inside such a machine, imagine designing a quantum system in which qubits are arranged so that their entanglement follows rules, similar to those found in holographic duality. In the holographic model, a simpler quantum theory living on a boundary generates a richer geometric structure inside. If this is how our universe works, then building a small version inside a quantum computer might reveal geometry in action. Physicists began exploring this idea by studying quantum error correction. Unlike classical errors, which simply flip a bit from 0 to 1 or 1 to 0, quantum errors are more subtle. They can distort superpositions and entanglement. To protect against these distortions, quantum information must be shared among many qubits in a way that allows the original state to be recovered, even if part of the system is disturbed. These codes create redundancy, not by duplication, but by weaving entanglement across the network. The remarkable discovery was that the mathematics describing these protections looks almost identical to the mathematics describing holographic spacetime. The same structure that prevents quantum information from being lost is the structure that allows geometry to exist. In a very real sense, a quantum computer protects its information by creating something like a tiny universe. Errors that would tear information apart act like tears in space-time. The correction rules stitch those tears, restoring the smoothness of the emergent geometry. Gravity itself could be interpreted as that stitching motion, ensuring that space-time remains coherent. This realization inspired a new kind of experiment. What if one built a system where the entanglement between qubits behaves like the entanglement believed to build spacetime? What if one could create the equivalent of a wormhole, a shortcut through an emergent geometry, using nothing more than quantum operations? The idea was bold. For many, it seemed like pure fantasy. But in the year 2022, that fantasy took its first small step toward reality. Researchers used a quantum processor to perform a special kind of teleportation. Quantum teleportation normally transfers information from one qubit to another by consuming entanglement. But in this experiment, the mathematical description showed that the teleportation process could be interpreted as information traveling through a tiny wormhole in the emergent spacetime. The wormhole was not a tunnel carved from real space. It was a path within the geometry created by the entanglement structure. The experiment did not bend physical distance. It bent informational distance. And bending informational distance is the essence of gravity. This result did not prove that wormholes are common in the universe, but it demonstrated something profound. Holographic spacetime is not just a theory. Its logic can be engineered. When quantum computers manipulate entanglement in the correct pattern, they can make geometry appear and disappear. They can create shortcuts and bridges. They can replicate the gravitational behavior predicted by holography. They can generate pieces of spacetime. If spacetime can be created in a laboratory, what does that say about the cosmos? It suggests that the geometry we experience might be continuously computed by the universe itself. The laws of physics might be algorithms running on a cosmic scale. The curvature of spacetime might be nothing more than the processing of quantum information adjusting to new conditions. Gravity becomes the update applied when the code changes. In this view, a black hole is not a mysterious pit in the geometry. It is a region where the code is compressed to its highest density. A star is not simply burning matter. It is entanglement patterns forming stable objects. A human brain is not only biology. It is a quantum system that manipulates information in extraordinarily complex ways. And when we build quantum computers, we are not merely constructing machines. We are constructing miniature realities. We are experimenting with the same tools that the universe uses to exist. There is another insight that comes from quantum circuits. When one maps out a specific calculation in a quantum computer, the flow of quantum information can be visualized as a kind of network. Some pathways are short and efficient. Others move through many steps and appear longer. The shortest pathways resemble geodesics, the paths that particles follow through curved spacetime. The computer, without being told anything about physics, generates the equivalent of a curved spatial structure simply by manipulating information. Geometry emerges from efficiency. The shortest path through the code becomes the straightest path through space. Quantum circuits reveal another important feature. When information becomes too scrambled, when the network becomes too chaotic, the emergent geometry breaks down. There is a threshold where space-time becomes no longer meaningful. This may explain the interior of black holes. Beyond a certain point, the entanglement becomes too chaotic to support a smooth geometry. The interior is not a place waiting to be explored. It is the collapse of the code into something spaceless. These discoveries lead to a breathtaking possibility. The universe might be one vast quantum error-correcting code. Every region of space-time protects the information it contains from being destroyed. Every gravitational effect keeps the code coherent. The reason nothing can escape a black hole's interior is that the encoding prevents local access to certain parts of the information. But that information still exists and emerges later as radiation. The rules of the code preserve the story even when the scenery changes. If this is correct, then the future of physics will be built not in giant particle colliders alone, but also in controlled quantum environments. We will learn how space-time reacts when we program different patterns of entanglement. We will learn what happens when information is rearranged in ways that nature has never attempted. We will learn whether new forms of gravity can be engineered, whether artificial boundaries can create artificial universes, whether complexity itself generates time. There could be a day when the first engineered space-time forms inside a device no larger than a classroom. A day when wormhole teleportation is no more surprising than a photon bouncing off a mirror. A day when the link between information and existence becomes direct and visible. Such a day would not diminish the cosmos. It would reveal our place within it more clearly. If we are made of information, then building systems that manipulate information at the deepest level means building systems that manipulate reality. The boundary between what is real and what is constructed would blur. Our understanding of universe and technology would merge. Quantum computers are not just tools for cracking encryption or simulating molecules. They are windows into the foundation beneath physics. In their qubits, we are beginning to see hints of the machinery behind space-time. In their gates, we see the logic that bends geometry. In their entanglement, we see the invisible threads that stitch reality together. Perhaps the universe is the largest quantum computer that will ever exist. And each human mind is a small quantum system exploring itself through curiosity. When we build quantum machines, we are teaching reality to understand its own language. The search for gravity's origin may end not in the heavens, but in the cold chambers of quantum laboratories. There, in silence deeper than the void between stars, space itself may flicker into existence for a fraction of a second, reminding us that reality is a computation always being written, always being corrected, always becoming. There is a quiet revolution happening in our understanding of the cosmos. It is a shift away from things and toward connections. For centuries, physics tried to describe the world by naming its ingredients, atoms, forces, fields. But the deeper we look, the more those ingredients dissolve into something abstract. A particle is not an isolated object. It is defined by the information it shares with the rest of the universe. A point in space is not a location. It is a position in a web of entanglement. Nothing exists alone. Everything is a relationship. This idea is known as relationalism. It proposes that the universe is not a collection of independent entities, but a network of interactions. Mass does not bend space-time by itself. The entanglement between matter creates the geometry. Time does not flow independently. The growth of correlations creates the sense of before and after. Even identity becomes conditional. A particle without its quantum links has no properties. The universe without relationships would be a blank nothing. To see how far this idea reaches, consider the simplest possible existence, a single qubit. On its own, it has no location, no orientation, no context. It might be in a superposition of 0 and 1, but without anything else to compare against. The distinction loses meaning. Now add another qubit. The pair can become entangled. Suddenly, there is structure. The two can share information. The relationship becomes the first hint of geometry. Add many qubits, and the mesh of interactions grows. Patterns emerge. Distances emerge. Space emerges. In this view, spacetime is not a background through which particles move. It is the set of possible relationships among quantum states. A region of high entanglement is densely connected and appears close. A region of low entanglement appears far. Motion is the changing pattern of connections. The universe is not in space. Space is in the universe. This idea dissolves a question that has puzzled philosophers since ancient times. What came first, space or matter? The answer is neither. Both arise together from information. Space is the structure of connections among bits of matter. Matter is the pattern of information stored in that structure. They are two different aspects of the same network. This network does not sit still. Quantum mechanics insists that systems evolve. Interactions shift. Information rearranges. The network grows in complexity as new correlations form. The result is time. The arrow of time emerges because entanglement spreads outward from every event. It is easier for information to become mixed than to remain isolated. The future holds more possible configurations than the past. That is why time feels like motion toward uncertainty. Gravity becomes the statistical behavior of this network. When matter gathers in one region, the entanglement around it changes. The network seeks to restore balance by adjusting the geometry. The motion of planets is not caused by an invisible force, but by the network relaxing into a smoother configuration. Gravity is the tendency of the universe to even out the informational load. This explains why gravity always attracts. There is no opposite to entanglement. There is only more or less connection. When two masses are near, their combined entanglement structure pushes the geometry inward. They fall together because their information wants to be organized more efficiently. Attraction is not a pull. It is the removal of inefficiency. The relational view also explains inertia. When an object moves without being pushed, it maintains its speed because the network of correlations around it remains stable. Changing the motion means changing the entanglement patterns. That requires interactions. A force is simply the act of rewriting the relationships that define motion. Even quantum fields, once thought to fill space like invisible fluids, become secondary to the underlying information. A field is not a substance spread throughout a container. It is a description of how entanglement responds when energy is added or removed. What we call a particle is a stable knot of information. What we call a wave is a ripple in connectivity. This new picture changes our understanding of the cosmos. The expansion of the universe may not be galaxies rushing apart through empty space. It may be entanglement stretching, increasing the space between regions as the network relaxes into a configuration that can support more information. Dark energy might not be a mysterious force. It might be the natural response of the quantum network to preserve relational structure as the universe grows. Even quantum measurement gains a new interpretation. When we observe something, we interact with it. We become entangled with it. We join the network in a way that fixes certain correlations. Before the measurement, the possibilities exist only in the relationships among parts of the system. After the measurement, the pattern has changed. We are not discovering new information. We are becoming part of it. There is something deeply human in this idea. Relationships define reality. Our lives are shaped by the connections we form. Our identities grow from interactions with others. Consciousness itself may be the integration of information across a network of neurons so dense and dynamic that it forms a unified perspective. If existence is relational, then we are woven into the same pattern that forms galaxies and black holes. The relational universe has no isolated pieces, no separate minds, no absolute space, only patterns of entanglement expressing themselves at different scales. Physics becomes the study of how these patterns behave. Cosmology becomes the study of the largest relationships. Quantum mechanics becomes the study of the smallest. And gravity becomes the geometry of the network as a whole. This is not mysticism. It is mathematics. It is the logical consequence of taking information seriously. The equations describing entanglement form graphs that look like lattices of nodes and links. When those graphs become dense enough, they approximate smooth geometry. The measure of connectivity becomes the measure of distance. The flow of information becomes the curvature of space. The stability of the network becomes the unbreakable law of gravity. Yet this understanding also reveals a fragility. If entanglement determines existence, then losing entanglement can make things cease to exist meaningfully. A region of universe cut off from all correlations with the rest would not simply be dark or inaccessible. It would be gone. Reality depends on communication. This returns us to a central truth. The universe is not a place where things happen. It is the happening itself. Every object, every event, every motion is a transformation in the web of information. Space is the shape of those transformations. Time is their ordering. Gravity is their harmony. In this picture, we are not spectators. We are participants in the ongoing computation of reality. Every thought, every decision, every exchange adds complexity to the network. Existence is a conversation the universe is having with itself, and gravity may simply be the grammar that keeps that conversation coherent. The oldest question in physics has always been, what is the universe made of? The newest answer is that the universe is made of relationships. Everything else is a consequence. If the universe is truly woven from information, then everything we call real is the result of a computation. Not a computation performed on a machine, but one performed by nature itself. The cosmos becomes a living algorithm, updating its own state from moment to moment. Particles interact because information must remain consistent. Gravity shapes spacetime because the network must preserve its structure. Time flows because information keeps changing. Every law of physics may be an instruction written into the code of existence. But code is not lifeless. When patterns become complex enough, they begin to organize. They begin to behave as though they have purpose. They evolve, and one day, they might become aware. In this vision, the Big Bang is not the explosion of matter from a point. It is the initialization of a quantum system in the simplest state possible. The early universe was a uniform field of information with almost no differentiation. But even the smallest fluctuations grew. Entanglement began to spread. The network expanded. Structures formed. Stars ignited. Chemistry blossomed into biology. Information began learning about itself. Every stage in this story can be described in terms of entropy. Where information is simple and uniform, entropy is low. As information becomes more complex and distributed, entropy rises. The universe is not running down into boring sameness. It is rushing upward into richer possibility. Order emerges not despite entropy, but because of it. Entropy is not the enemy of complexity. It is the driver of complexity. Gravity is the sculptor. It pulls matter together, raising temperature and enabling nuclear reactions. It gives birth to stars that produce the heavy elements needed for life. It forms galaxies where those stars can gather. It creates black holes that recycle information. The gravitational universe is not hostile to life. It is the stage that makes life possible. Gravity is information arranging itself into ever more intricate forms. If one follows this logic, the universe begins to look like a self-organizing computational system, striving to explore every configuration it can reach. Dark matter and dark energy might be aspects of the information architecture that we barely understand. The quantum vacuum might be the memory store that holds the holographic code of space-time. The cosmic horizon may be the boundary where this code is written. What then is consciousness? Consciousness could be the universe becoming aware of its own information. A brain is not special because it is made of rare materials. It is special because it forms a structure capable of storing and processing information in a way that reflects upon itself. Awareness may be a pattern of entanglement so complex that the network generates a point of view. The cosmos looks at us through stars, but we look back through eyes and neurons built from those same stars. The observer and the observed are parts of one computation. This does not mean life was planned. It means life was allowed. The rules of quantum information create a world where complexity can grow, where order can form, where minds can evolve. We are not exceptions. We are expressions. There is a philosophical question that arises from this picture. If everything is computation, could the universe be simulated? Could another world have built this one? The answer is subtle. Simulation implies a higher level of reality with its own information. But if information is fundamental, if there is no deeper substance beneath the code, then our universe does not need a substrate. It is not a program running on a larger machine. It is the machine. Existence does not require an operator. It requires only consistency. The laws of physics may be the rules that guarantee consistency. They prevent contradictions. They preserve information. They ensure that the code can evolve without breaking. Even randomness could be part of the program. Quantum uncertainty adds variety to the network, allowing novelty to arise. Where does this leave the human desire for meaning? It elevates it. If the universe is a computation generating all possibilities, then meaning becomes the patterns that persist through time. Love, curiosity, knowledge, creation. Each is a structure in the informational network that outlives the chaos around it. Meaning is information that resists decay. When we learn, when we share ideas, when we build societies, we increase the complexity of the universe. We participate in the growth of reality. The mystery of gravity brings us to this profound realization. Gravity seemed like a force that pulls objects downward. Now, it looks like the tendency of the universe to organize itself. Gravity is the subtle signature of information trying to remain connected. It is the promise that no part of the universe will be left behind. Even in the cold void between galaxies, the network persists. Even inside a black hole, information is preserved. There are still unanswered questions. How exactly is spacetime encoded on the boundary of the universe? What mechanism gives rise to mass and energy from pure information? How does consciousness interface with the entanglement network? And what happens when the universe reaches the limits of its computation? These questions do not weaken the idea. They show that we are standing at the threshold of a deeper understanding. We have learned that matter is not fundamental. Space is not fundamental. Gravity is not fundamental. Information is fundamental. Everything else is a consequence. We began by asking why gravity refuses to behave like the other forces, why it cannot be quantized in the usual way, why it always attracts, why it is so weak, why it defines the shape of the cosmos. The answer is that gravity was never a force. It is a phenomenon that emerges when information organizes itself into a geometry smooth enough for existence to make sense. The apple does not fall because the earth pulls it. The apple falls because the informational network bends to remain whole. The planet orbits the sun because the code demands stability. The galaxies cling together because the universe refuses to lose coherence. Gravity is the visible effect of invisible rules written into the source code of reality.